Every time you see an electric car just glide silently down the street, you're not just looking at a piece of modern tech. No, you're actually looking at the final product of billions of years of unbelievably powerful and sometimes violent geological forces. So today, we're going to dig deep, really deep, to connect the green technology of tomorrow with the ancient, unchangeable blueprint of our planet. Okay, so let's jump right in with the big question, the one that kicks off this whole explainer. We all tend to see electric vehicles as this clean, green solution, right? The answer to our fossil fuel problem. But what if the story is just a little more complicated than that? What if the real answer isn't on the road at all, but buried deep within the Earth's crust? And here it is. This is the core trade-off. On one hand, yeah, EVs are a massive win for cutting down our use of gasoline. That's the big promise, the reason we're all excited. But on the flip side, building them requires this special cocktail of really scarce metals. I'm talking about stuff like neodymium, which makes the powerful lightweight magnets in the motors possible, and lithium and lanthanum, which are absolutely essential for those high-performance batteries. And believe me, this isn't the kind of stuff you can find just anywhere. And of course, getting those metals out of the ground, well, that comes with its own hefty environmental price tag. Mining can tear up landscapes, mess with animal habitats, and lead to serious soil erosion. But what's really scary is the potential for water contamination. We're talking about something called acid mine drainage, which can create water so acidic with a pH of 2.5 or even lower that it can literally dissolve metals and poison entire ecosystems for generations. So all of that brings us to the really big question. Why? Why are these critical minerals so rare, and why are they all clumped together in just a few spots on the entire globe? To get to the bottom of that, we have to rewind the clock, way, way back. Just try to picture this. It's 4.6 billion years ago. Our planet isn't the blue and green world we know. It's a chaotic, glowing, molten ball of rock, just starting to form from a swirling cloud of cosmic dust. And nearly every single element we use today, from the iron in our own blood to the lithium in our phone batteries, had its destiny sealed in these first fiery moments. And this, right here, is where the whole story of scarcity really begins. As this ball of molten rock started to cool down, this incredible sorting process began to happen. The heaviest elements, think iron, they sank toward the center. Meanwhile, the lighter stuff, like silica, floated up towards the surface. This is the fundamental reason our planet's resources are not just some evenly mixed soup. So let's break it down. First, right at the center, you have the core. All the heaviest materials, we're talking mostly iron and nickel, sank straight to the middle, forming this super, super dense ball. Sitting on top of the core is the mantle. This is a massive layer of molten rock we call magma. And it's not just sitting there. It's constantly, but very slowly, circulating in these giant loops called convection cells. Now remember that detail, that circulation, because it's basically the engine for everything that happens up here on the surface. And then, finally, we get to the lithosphere. This is the planet's brittle outer shell. It's the ground beneath our feet. It's about 100 kilometers thick, and it includes the crust, plus the very top solid part of the mantle. The best way to think about it is like a cracked eggshell that's floating on the hot, gooey rock below. Okay, so we've got this layered planet, but that cracked eggshell we're living on, it's not sitting still. Not at all. And its movement is the key to the grand unifying theory of all of geology. Let's travel back to 1912. A meteorologist, of all people, named Alfred Wegener, comes up with this truly revolutionary, mind-blowing idea. He suggests that the continents aren't fixed in place, but are actually drifting around. He even said that they were once all connected together in a giant supercontinent he named Pangaea. Now, at the time, pretty much every other scientist thought he was completely out of his mind. But Wegener, he had evidence, and this is a brilliant example of one of his biggest clues. Fossils of this small, freshwater reptile Mesosaurus were found in South America and also in Africa. Now think about it. How could a little reptile that only lived in freshwater possibly cross the enormous, salty Atlantic Ocean? The simplest answer? It didn't have to. The coastlines where those fossils were found were once joined together. Wegener's crazy idea eventually laid the groundwork for what we now know as the theory of plate tectonics. This theory explains that the Earth's lithosphere, that brittle outer shell, is broken into a bunch of massive plates, and that these plates are in constant, slow-motion movement. So what's pushing these continent-sized plates around? Well, it's that engine we talked about earlier. The intense heat from the Earth's radioactive core creates those huge churning convection cells in the mantle.
Hot magma rises, it cools off near the surface, and then it sinks back down. This slow, powerful circulation literally drags the tectonic plates that are floating on top of it. This whole thing creates a continuous cycle of creation and destruction. You have new crust constantly being born as magma bubbles up at seafloor spreading zones. And at the same time, older, denser oceanic crust gets pulled under the lighter continental plates, a process we call subduction, where it literally dives back down into the mantle to be melted and recycled all over again. Now, this constant grinding motion of massive plates has some pretty dramatic consequences. So, what actually happens at these boundaries, these places where continent-sized chunks of crust are crashing into each other? Well, for one thing, earthquakes and volcanoes are not random events. Not at all. They are the direct result of plate tectonics. If you were to map them all out, you'd see they form these very distinct lines, almost all of them right along the edges of these plates. The most famous example, of course, is the Ring of Fire, a zone of intense seismic and volcanic activity that wraps all the way around the Pacific Ocean. So, how fast is all this action happening? On average, it's about 1.4 inches per year. I mean, it's an almost imperceptibly slow process, about the same speed that your fingernails grow. But when you give it millions of years, that slow, relentless movement can shift continents, raise up massive mountains, and create entire oceans. But here's the thing, this movement isn't a smooth glide. The jagged edges of these plates snag on each other, they get stuck, and they build up incredible amounts of energy. An earthquake? Well, that's the exact moment all that stored up energy is violently released. A sudden, massive slip that sends shockwaves ripping through the crust. But plate collisions can also be constructive, in a way. When two continental plates slam into each other, the crust has nowhere to go but up. And this is exactly how the world's most massive mountain ranges, like the incredible Himalayas, were formed. A slow-motion collision that is, believe it or not, still happening today. Okay, so let's bring this all the way back around to where we started, that electric car. How does this epic, billion-year story of planetary formation and moving continents connect to the stuff that's inside a modern battery? Well, here it is. This is the crucial connection. The very same violent forces that cause devastating earthquakes and build towering mountains are also nature's refinery. Just think about it for a second. Seafloor spreading basically dredges up important metals like copper and lead from the mantle. Volcanic eruptions act like elevators, shooting rare elements up to the surface. And the immense heat and pressure from colliding continents, it literally cooks and concentrates these elements into the rich veins that we can then mine today. And that brings us to what might be the most profound and sobering reality of this whole story. A quote from our source material really says it best. The elements and minerals that were present when the planet formed are all that we have. We're working with a finite supply. There's no making more of it. So when you put it all together, the geology of our planet has handed us both the raw ingredients for a green future and a very strict set of limits. The critical question for all of us isn't if we should transition to new technologies, but how. How do we do it, knowing that every single battery, every single motor is fundamentally tied to this ancient, finite, and incredibly powerful planetary blueprint?